Hello everyone, my name is Heido Samaras, and on behalf of my colleagues and co-authors of this paper titled Identifying Core Issues in Concept Maps, I'm going to be making this presentation to you. Let me begin with a definition before I move on to an initial observation regarding the clarity of substructures of a concept map. A concept map is a graphical tool for organizing and representing knowledge, theories, or parts of our real world. Concept maps are diagrams that show the relationships between elements, that is, between concepts. However, the reality we are called upon to comprehend and to express does not directly emerge from the connections among the elements, but from the connections of structures which consist of elements. Marvin Minsky's view is in agreement with our own initial observation, that is that the higher the expertise of a person who creates a concept map, the higher the clarity of substructures in the map. In this paper, we define as a core issue every distinctive part of a concept map, every substructure, containing significant information content. A strictly hierarchical concept map contains a root concept and various links which form branches. These branches are resolved in sub-branches, etc. However, a branch does not have a rich internal structure since, in this case, there is only one way to connect nodes. Cross-linking is necessary for the creation of rich structures. It's worth pointing out that established systems for assessing concept maps recognize the value and significance of cross-links. In addition, it is widely acceptable that valid cross-links express the creativity of the concept map creator. In this paper, we attempt to justify the position that there is indeed great significance in crosslinks, since they comprise the necessary element for the formation of structures. Crosslinks, in fact, have a great value as a necessary type of link for the creation of structures. Having discussed the theoretical background, let me move on now to discuss our methodology. In this paper, we investigate the extent to which the structures in a concept map, which result from applying pure topological criteria, are the real core issue of that map. In other words, we investigate if the structurally determined groups of concepts are also semantically appropriate in order to be characterized as core issues, and also we investigate how this relates to their categorization, which was based on the expertise of the people who created each map. We use concept maps from various fields and with various numbers of concepts. These concept maps, which are presented as typical concept map examples in various research papers, were categorized based on the expertise of the people who created them. For the determination of the structures, we use the Newman-Girvan algorithm. The algorithm for determining structure comprises the following steps. First, count the shortest distances between all pairs of nodes. Second, calculate the number of shortest paths that pass through each edge. Third, find the edge with the greatest number of paths and delete them from the network. And fourth, after deleting, repeat step 1. When we find and delete the edge with the greatest number of shortest paths, we gradually form paths, that is, structures, using as a criterion the maximum information flow. The edge with the greatest number of shortest paths is the edge with the maximum information flow. Indeed, this is what we try to achieve in order to define the structures. The maximum flow of information cannot pass through the edges that belong to a core issue, but from the edges that connect the core issues, since these edges connect loads of structures rather than loads of concepts. So let's take a look at an example. This is a concept map from the paper titled On the Use of Concept Maps as an Assessment Tool in Science, What We Have Learned So Far. Due to the small size of this map, it is easy to see that it has one structure and two nodes connected to the structure. The structure consists of the node's graph, linking lines, nodes, and linking words. We could name the structure graph. According to this figure, if we are thinking on a somewhat more abstract level, we could say that a concept map is a graph where the nodes represent concepts. This result is also confirmed by the algorithm. Indeed, when we apply the previous algorithm, we get this separation, which is also semantically correct. Here's a second example. This is a concept map from the book titled Knowing What Students Know, The Science and Design of Educational Assessment, and characterized by the authors of the book as a typical example of a novice concept map. When we apply the previous algorithm, we get two structures, the structures that are separated by the bold line. It is easy to see that they are also semantically valid. The first one expresses the block and the second the plane. However, the development of structures is quite far from the optimum, and the same holds for the semantics. In this third example, we see the map of an expert. This is also a concept map from the book titled Knowing What Students Know, The Science and Design of Educational Assessment, and characterized as a typical example of an expert concept map. Similarly, when we apply the previous algorithm, we get two structures, the structures that are separated by the bold line. The first one expresses the plane, and the second the principles we have to apply. In this case, the development of structures is perfect, and the same holds for the semantics. Between the previous two concept maps, why is the expert's concept map better than the map of the novice? It is easy to see that experts develop maps in a semantically more fertile way. But how could we compare maps on the level of structure? As a criterion, we could determine the difference the two structures proposed have from two supposed structures with exactly the same nodes, in which, however, the links, and here we are referring to the same number of connections, randomly occur among the nodes. The further away from the random the structures are, the better they can be considered to be. Applying this criterion, the map of the expert does indeed prove to have better structures than the map of the novice. I come now to our results. The algorithm we used finds natural divisions among the concepts without requiring the user to specify how many structures there should be or placing restrictions on their sizes. This requires an active role on the part of the student who, based on feedback received from the method, should evaluate the semantic validity of the proposed structures. For each map out of the 45, the method may also have given one or more ways of separation into structures which were not semantically valid. However, one or more of the separations given for each map was valid in 41 out of the 45 cases of concept maps. Our results lead us to the following considerations. The development of a mental construction cannot be accomplished effectively and efficiently, as has been proved, even in quantitative terms by Simon, without the use of modules. Therefore, it is crucial to find ways to guide the learner through this process. The presented method gives feedback regarding the structures contained in the map. We could exploit this method in order to guide the learners to apply a structured approach in developing their concept maps and not to follow a chaotic way of connecting concepts. Moreover, it would be worthwhile to consider in the future the extent to which the guidance provided to the student in order to develop the map in a structured way could simultaneously lead to semantically better choices. So this brings me to the end of the presentation. The research project that just presented is being implemented within the framework of the action supporting postdoctoral researchers of the operational program Education and Lifelong Learning, and is co-financed by the European Social Fund and the Greek state. On behalf of my colleagues and co-authors, I would like to thank you for giving us the opportunity to present our work at the Future of Education International Conference. Thank you very much.